Minnesota, of course, has frac-sand mining too. And this is one of the maps that's available. Iowa does not have a map. I looked all over for a map of fracking in Iowa, and maybe the Alma people can help me get one later.
There's only one mine in there.
Jeff said earlier there's only one in Iowa, and that's at just outside of Missouri.
I see. So basically, it's not worth making a map because we just have one. Oh, I could have stuck it on the Wisconsin map down below across the river from it. That would have worked, I guess. Okay. Just a very brief thing about how the sands formed in the first place. And we have to understand that close to 100 million years was the amount that was required for nature to build the frac sands. 100 million years. Humanity's only existed for 2 million years, just to give us a little bit of context. When they were forming, we were south of the equator. This area was south of the equator, and for the entire time that the sands were being developed, North America was covered by a shallow sea, no deeper than, say, 100 feet. Continent was very stable, except for its very slow, maybe 1 or 2 inch a year migration towards where we are now. All that we had was a continent covered by a shallow sea. Sometimes some areas would be above sea level, and sometimes they wouldn't. The sands ultimately come from what is now Canada. Granites had to be broken down, had to be totally weathered, and all of the less stable minerals had to leave, leaving only the quartz. The quartz itself, I'm getting ahead of myself here. These are the rocks that we're talking about. There are rocks, well, I think I have the ages given here. From the oldest formations are about 5,500 million years old. The youngest are a little bit more than 400 odd million years old. And if you look at, a geologist can look at the maps and give you, can look at the rocks and can give you some idea of how deep the water was when the rocks formed. And I won't go into details except to show you that I'll be building a curve for how deep the water was over time, and to the left is deep and to the right is shallow. And this is basically what happened. The greatest depths, again, no more than, say, 100 feet. The important thing is that the Wanawak was above sea level when it was formed. That's very important. And how do we know that? You see those little marks on either side, the little, those indicate what we call cross-bedding, which are nothing more than fossil sand dunes. Those sand dunes say that the area was above sea level at the time the Wanawak was formed, and also when the Jordan sandstone was formed, and when the St. Peter sandstone was formed. All of those are the three main targets for frac sand miners. And it's no accident that these are basically dune sands that they want to mine. The reason why the sands had to be above sea level when they were grounded was because if you have sand being pushed around underwater, either in a river or in the sea, the sand grains can't bang into each other effectively to round each other out because they're cushioned by water. If they're above sea level and the wind is blowing them around, the sand grains can be picked up and flung against other sand grains, and they round each other off. And you can repeat this many times. It wasn't just once that these sand grains were above sea level, but several times. And the more time spent above sea level, the rounder they get. This shows the sizes of the sand you're interested in either in the screen mesh size or the millimeters or inches. The important thing is that the sand that Frac-Sand miners are interested in are something like 300th to 100th of an inch. So if you wanted to set up a 1-inch line of these grains next to each other, there would be 30 to 60 grains. That's about the size of it. I have some Frac-Sand here, just in case your hatred for fracking won't prevent you from handling a piece of Frac-Sand. Here it is. And if you want to, I have we call them a geologist lens, but these they're also called a jeweler's lens. You have to put it up against your eye and then bring it until you can see. If you do that, you'll see that the sand grains are round. Quartz is very durable, very tough, very hard, chemically fairly inert, and if it's round, all of those properties make it good for fracking. It's important to have them round because when you are fracking, when you're exploding the rock underneath the ground, you want the sand to come up into the fractures and hold them open. If they were angular, they would hang up. You want them to come in like ball bearings. That's why round is so important. Wisconsin is apparently exporting Frac-Sand to Saudi Arabia. And people don't understand why. Well, Saudi Arabia, that's desert. They got lots of desert sand. That desert hasn't been around for 100 million years. That's the big difference. So again, hard, tough, chemically durable, and round. This is a chunk of granite. I have a chunk of granite here. I could pass it around, but I guess I won't. That picture's good enough. Anything that isn't quartz gets over the tens of millions of years broken down and nothing's left but quartz. Now, a couple of things here. First of all, when we talk about an aquifer, it comes from the Latin for water and bearing, water-bearing, aquifer. Just like Christopher, Christ, he's the guy who ferried Christ across the river. So he was the Christ bearer, Christopher, right? Aquifer, water bearer. Contrary to common thought, most aquifers, the water in the aquifers are not in large holes in the ground. The water resides between grains of sand. And so one of the consequences of this is water will flow very slowly in and out of an aquifer. You measure that rate of speed in terms of only inches to feet per day. In the driftless area, we have karst topography, and that's where water can go a lot faster because we have underwater streams. But that's a very special condition. Our aquifers are sand aquifers, and our aquifers, the water moves very slowly. And that's one of the consequences of this is that if you pollute an aquifer, you basically pollute it forever. So you have to protect your aquifers at all costs. So the Wanawak and Jordan and St. Peter sandstones are all great aquifers because their grains are round and there are many zones in which the grains are all the same size. And if they're round and all the same size, you maximize the void space between the grains that can be occupied by water. Does that make sense? So here's a Frac-Sand mine. One of the first things is that a mine will use hundreds of thousands of gallons of water a day, and that was touched upon earlier this morning, where you can either get the water out of surface streams, which will of course cut down on the amount of water in the streams, or you can pull it out of the ground using high-capacity wells. So you can deplete surface water and groundwater, and we just finished a drought year. So that's really important to know. The second thing is, we are in a time of climate change, which means that there are going to be great extremes. Some years, very rainy, some years very droughty. And we don't know how long each drought would persist. What this means is that the Frac-Sand mines would be competing with the water people need to drink, the water people need to farm. That's very important to know. Beyond that, there's also the problem of contaminating the water. And this, I just watched the price of sand thing, and I was cussing the whole time because man was lying through his teeth. The guy representing the Frac-Sand miners was lying through his teeth. This is the DNR link if you want to learn about silica sand mining in Wisconsin as of January 2012. There's nothing later. It makes a good point between the lines. DNR, traditionally, and it doesn't matter if you have a Democrat governor or Republican governor, DNR basically makes rules to control industry by asking the lobbyists for that industry to come in and help them write the rules. And that's the truth. I suspect it's probably the same in Minnesota, from what little I know. I can't say anything about Iowa. But this little thing here makes no mention of flocculation or flocculants, which is the most dangerous thing that can be done to either surface or groundwater. I have to say that both the Wisconsin Geological and Natural History Survey and DNR are basically proponents and apologists for Frac-Sand mining. You can't see it any other way. And again, it could well be the same for Minnesota, and I can't speak for Iowa. They had a conference October 13th, 2011, and this is the propaganda with which WGNHS basically pimps for the silica sand mining industry. So if you see a blue, background like that, spoiler alert, it comes from the state proponents for Frac-Sand mining. This is one of the things they're saying. Wisconsin has a history of industrial sand mining. Has recorded very few problems in 100+ years. First of all, this is not Frac-Sand mining. This is not at all. And the second thing is, the magnitude of Frac-Sand mining is like on the order of 100 times more than it was before the Frac-Sand boom. And just the quality of a boom means poorer and poorer regulation, more and more urgency, because if something, as the industry continues, problems are going to arise, and they're going to arise, and at some point the problems could be so great that they will be forced to stop. So they have to hurry, 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 hurry. Same for fracking, same for Frac-Sand mining. This again is from the state. They downplay groundwater use and potential for contamination. The biggest contaminant is flocculants, and I'll talk about them in a little bit. They barely mention what flocculants are. Flocculants are an additive that you add to murky water in order for the fine material to clump together into larger aggregates that can then settle out faster and can be removed. So what they do when they're washing the sands is they add a flocculant. The principal flocculant is something called polyacrylamide, and keep that in your heads because that is the thing that may possibly kill your kids and or your grandkids. With any luck, you'll be dead before you're hit by it. By training, I'm a sedimentologist. I study how sediments are formed, how they move, how they settle out. And one of the things we'd always do is we would use flocculants for our own lab reasons. But what the flocculant does is this. Here are the very fine grains. They're so fine they remain suspended in the water for a long time. And if you add a flocculant, you make floccules. And a floccule is a clump of tiny grains that have aggregated together so that, again, they can be settled out faster. So you add a flocculant to the dispersed sediment, and you wind up with clear water, and all of the floccules have settled down below, and you can remove them. I keep getting ahead of myself. These are how they look magnified. So the 100 microns would be something like a tenth of a millimeter, very small. And I spent about 2 hours making this thing. And here's a flocculant polymer, greatly magnified. And what it basically does is it attracts all the whole bunch of particles so that they act as one unit and they can fall out. Just simple-minded chemical terms. Poly means many, right? As in polygamous, right? Mer means unit. A monomer is one unit. A polymer is something made up of many monomers. This is acrylamide. It's a monomer. It's the building block for flocculants. And what you do, oh, by the way, you worry about acrylamide because 5 minutes?
Or a little more. Wait a minute.
Okay.
A little more.
Acrylamide is a carcinogenic neurotoxin. Here is a polyacrylamide, except just one small chunk of it. You can string like 15 to 30 million monomers or acrylamides together to make one of those strings. And that's what you use as flocculant. The question then is, if you ever look at a polyacrylamide that you buy commercially, you'll always find some acrylamide with it. And the question is, why is it there? Did it bond incompletely when they were making the polyacrylamide, or did it break down after it was made? But maybe more important than that, is, can polyacrylamide degenerate into acrylamide in soil streams and groundwater? The guy in the movie basically said, no, it can't, don't worry about it, it'll break down before you know it, no problem. And when people bring it up, people have actually been abused verbally for daring to suggest that polyacrylamide can degenerate. Well, let's look at some science on that. First of all, we know this thing, I mean, but if you look at an environmental threat, if you suspect something, it's guilty until you prove otherwise, because once you do it, once it's in the system, it'll be too late if it's bad. There's in more droughty areas, like in the western United States, they actually sell a thing that you can add to your soil that'll hang on to water and release it slowly. They call them polyacrylamide hydrogels, but it's a very dangerous practice. Linda Chopper-Scott wrote, she's a very good person on the science of gardening, and she says basically, hydrogels degrade after 2 to 5 years, exposed to fertilizer salts increases the rate of degradation. When hydrogels degrade, one of the byproducts is acrylamide, and it can be absorbed through the skin or by inhaling. So what she's saying is, if you're gardening with this stuff, you better wear gloves and a mask. Now, who wants to garden that way? Link to her stuff here, if you want. And you can come up to me afterwards if you can't do it long enough. This is another one. Eldon Smith and Susan Proust and Frederick Olming are all very reputable scientists. Those are their organizations. And this is what they say. They ran experiments under environmental conditions, in surface water or in groundwater, and they find that polyacrylamide can degrade to acrylamide under environmental conditions. In every case, in every environmental simulated environment they used, it happened, except when you dry the solutions totally, which of course won't happen in surface water or in groundwater. And finally, another source from agriculture and food chemistry by a bunch of people who are well accredited. And what they say is basically the stability of polyacrylamide is concerned because of the possibility of acrylamide monomer release during environmental weathering. Aqueous solutions of commercial polyacrylamide mixed with ferrosulfide subject to stimulated and natural sunlight irradiation showed polymer chain scission, yes, I mean the same word as scissors, right? And release of the acrylamide monomer. And so there is scientific basis for being very wary of polyacrylamide being released into your environment. And I was given 5 minutes, and that's about it. Yes, sir. So you first.
Can acrylamide be a marker to prove water contamination from a mine or a fracking well? Does acrylamide end up in the sand that's going to the fracking well, or do they use?
Well, I would say that if sand washing is in practice at a site near you, check your well. If you'll find acrylamide in it, you are basically verifying the fact that it more than likely came from the breakdown of polyacrylamide.
And that is it used also in fracking wells when they're?
Yeah, they also use it in fracking itself, and that's another concern in the areas which have the tight oil shales.
And that would be also a marker if you had it in your well, and there's a.
I would think so, but I've not been operating directly with the frackers themselves, although I do know a little bit about it.
Mm-hmm.
Yes, ma'am.
Can any place where you have your water tested, can they test for acrylamide?
I don't think so. It would cost you a bunch of money.
Oh.
They only do fairly standard tests. They always do nitrate, nitrite. They always do some of the herbicides, but you would probably have to pay special for it. So I would suggest recruit an ally in a chem lab somewhere who would be willing to work for you.
Would a high school it's not already, is there a standard set in parts per million or parts per billion of acrylamide where a certain aquifer would be considered contaminated?
There are, but I can't give you that number. There would have
But
to
it
be.
doesn't. And are there any studies that show that there is, are there studies on the other side that are peer-reviewed showing that there is no danger of breakdown of polyacrylamide?
No, the industry has no peer-reviewed studies other than from people that they themselves hire. Okay?
Of course.
And that's the truth. That's the same for crystalline silica.
Dr. Rodolfo, you talked a little bit about the groundwater or the bedrock, but it seems like we've got sort of three situations. I think I'm inferring a little bit from what you were saying, but you talked about sandstone aquifers, and you talked about karst topography, and I would understand that most of the driftless area is underlain by karst topography.
Yes.
And that there are some areas, say in the north end of it, where the Chippewa-Barron County, where there's more sandstone involved. But you've also got that area to the east of Toma, in the area where they're doing sort of a cran sand mining. Is that a different kind of groundwater situation there than you'd be dealing with in the karst topography in the sandstone areas?
No, the driftless area is pretty much underlain by almost horizontal rocks. I can show you a column, a stratigraphic column from Wisconsin, and you can translate it to Minnesota and Iowa, except for the fact that it's tilting delicately toward the west and a little bit toward the south. I think in La Crosse, you go 1 mile, it goes down 14 feet. So that's very gradual, you can't even see that. Well, what this is saying, I keep telling people in Minnesota, Iowa, and Illinois, if we Wisconsinians pollute our aquifers, guess what? We're polluting yours as well.
Well, the area to the east of Toma isn't generally considered to be driftless. That's glacial runout area, isn't it? Where the sandberg.
Oh, I'm sorry, east of Toma, yes.
That's not bedrock mining. That's already glacially different.
That's glacial, but that's not what they mine for Frac-Sand. You don't mine that for Frac-Sand.
It's a mine in Wyville.
You can mine the Bible?
Wyville,
Oh,
near Toma. I have a question. I've just heard rumors that they use, organic phosphates to speed up the flocculation process. Is this?
that's basically what their scientific gardening, I can't remember that names. That's basically what she says. In the presence of fertilizers, you speed up the breakdown.
Okay, but I just heard they have, okay, purely rumors. I have a photograph of a truck transporting them, but that they're using that in mining also.
You also have to consider what happens after they flocculate, because they take that stuff and what do they do with it? If they put it back in the pond, what's that do to the groundwater underneath the pond? If it dries out and the wind blows, what happens to the fine grains that you flocculated? They break down and then they blow in the wind. All of these I think are concerns.
Could the testing for acrylamides be done in a high school, or is that the?
I'm not enough of a chemist to know that. In fact, I'm an organic chemist. As a geologist, most of my chemistry is inorganic. But yeah, I asked high school, okay, that's it, I'm told to. Thank you.